Walk down the aisle of any tackle shop, and you'll find hundreds of lures designed to rattle, clack, and pop. The design logic is simple. A louder bait should create more noise to attract predators in murky water. But looking at this vector diagram, we see the reality of aquatic physics. Because fish are largely composed of water, they share a nearly identical acoustic density with their environment. Sound pressure waves pass through their tissues without encountering a physical barrier to bounce off of. Since the body doesn't deflect the sound, those waves travel through the animal invisibly. The internal sensory pathways remain completely undisturbed by the acoustic noise. You can drag a high-decibel rattle directly past the head of an apex predator and receive no response, no reflex, and no strike. Relying on acoustic noise assumes that fish hear the same way humans do. In reality, sound pressure is often a ghost in the water. Contrast that with a silent, smooth-sided swimbait entering that same dork environment. It creates no acoustic noise at all. Yet, as it glides through the darkness, a predator emerges from the shadows. It intercepts the bait with calculated, violent precision. The trigger wasn't sound. As the silent lure moved, it physically shoved the dense water aside, creating a mechanical disturbance that the fish felt. The underwater hunting ground is governed by hydrodynamic pressure. Physical displacement provides the information, making acoustic noise irrelevant to the strike. Water is nearly 800 times denser than air. Any object moving through it must physically pry the molecules apart to make progress. This schematic maps the invisible results of movement. As an object travels, water rolls off its edges, leaving a specific hydrodynamic footprint, a ladder-like trail of swirling currents called a vortex streak. These shift waves oscillate within a low-frequency window, between 1 and 200 Hz. While acoustic sound is a high-frequency vibration, these shift waves are a heavy, physical pushing action. They represent a tangible mass of water being moved through space. Any moving body, a lure, a fin, or a tail, creates a measurable deformation of the water column. It turns movement into a physical trail. To detect these heavy shift waves, fish evolved the lateral line, a sensory network specifically tuned to feel the movement of water. If you look at the flank of a fish, you can see a row of small pores. These open into fluid-filled canals that run horizontally along the animal's body. Inside these canals sits the neuromast. It consists of sensory hair cells topped by a flexible, gelatinous dome called a cupula. When a pressure wave from a lure pushes water into the canal, that internal current physically bends the cupula to one side. This bending serves as a biological analog to digital converter. The mechanical force of the moving water is instantly translated into an electrical neural pulse. The neuromast allows the fish to feel the shape and movement of objects at a distance, turning water pressure into a sense of touch. On the macroscopic level, a fish isn't just detecting one point of data. Thousands of these neuromasts are firing simultaneously across its entire body. As a disturbance moves past, the brain aggregates these thousands of independent electrical pulses in real time. By comparing the timing and intensity of the signals, the brain can triangulate the exact distance, size, and speed of the object. It creates a geometrical map of the displacement. This resulting mental construct is a hydrodynamic image. It provides the fish with a three-dimensional tactical map of its environment. This system turns pitch-black water into a navigable environment. Even when vision fails, the data from the water column is constant. This real-time map enables wake tracking. A predator follows the specific path of an object that has already moved out of the immediate area. A predator's lateral line can detect and follow a specific vortex trail up to 10 seconds after the prey has passed. The fish is effectively hunting a ghost, following a physical trail of displaced water over distances that vision could never cover. For the angler, this shifts the focus to the physical volume of the lure. The specific rhythm of displaced water is the primary input its sensors are designed to receive. Survival relies on how precisely you manipulate the dense, physical web of the water column.